Welcome back to Mechanical Systems Design. In this video, we will discuss electric motors, how they work, how we model them, what their important characteristics are, how we can incorporate them into our designs, and how they behave in some special conditions. So you'll want to read the topic reading carefully first. This is all new territory. And we'll have some exercises later. So you want pencil and paper and a partner to get the most out of it. So first, we're going to review the model. And since it's new stuff, we'll spend a bit more time than usual going over the topic reading. We'll be applying these ideas in the next 3 projects. So you want to make sure they're super solid. And if there is nothing else that you remember from this video, let it be these 2 things. In an electric motor, the electromechanical torque is proportional to the current through the coil by the motor constant. And there is a voltage, we call it back EMF or electromechanical voltage, that is proportional to the speed of the motor, also through the motor constant. And these are the same thing. And to understand why this happens, sometimes that helps us to solidify this knowledge. We can think back to some concepts we learned in Physics 43 or E40 in our electromagnetism modules. And it all comes from this phenomenon that if you have a magnetic field and there's a wire in it and you run a current through the wire, that induces a force that tries to make the wire move. And the magnitude of the force will be proportional to the magnetic field strength, the current, and the length of the wire. Now, why does this happen? It just is. This is part of the nature of the universe. We don't experience these electromagnetic effects directly in our daily lives that much, although they're used in tools all around us. So sometimes we don't have a strong intuition for it, but this is just a fact like gravity or inertia. So that is the reason that as we increase the current through our motor, the torque increases. Now there's a matching effect, which is that if you take a wire and you move it quickly through a magnetic field, that tends to cause the electrons to move. There's an electrical potential pushing the electrons. There's a voltage. And the magnitude of the voltage, again, will depend on the strength of the magnetic field, the length of the wire, and how fast the wire moves. And that is why this back EMF, or this electromechanical voltage drop in your motor, is proportional to speed of the motor. Now, to get really to rotational speed and torque from this force and linear velocity, we can think about what's happening inside the motor. It's inconvenient to have a very long actuator. You like something that's more compact. So to achieve this, people take the wire and make a loop. And actually, in a real motor, there will be lots and lots of loops that form the coil. And on this part of the wire is on this side of the axis. And when the electrons flow through, we get a force down. And those same electrons will eventually go over here. They'll flow the opposite way, and it'll cause a force up in the same magnetic field. But they have opposite lever arms. And so they cause this thing to tend to spin. They produce a torque. And similarly, when you spin it, that moves the the wires through that field and induces a voltage. Now, a real motor is a little more complicated than our simple diagram, but it really, even though it looks complex and there's lots of little practical details that have to be right, it all operates on that same principle. You've just got lots of wires wrapped in, and there's an armature to enhance the electromagnetic effects, and there are magnets on the outside, and the case of the motor helps enhance some of the magnetic effects. But really, all we're doing is we've got wires that are in a magnetic field, we run a current through them, and that causes them to want to move. And then as it spins, that causes this voltage. And with this big complicated thing, it would be hard to like measure the length or the magnetic field strength as that's changing as you move through the space, and so is the radius, which gets you to torque. But fortunately, we can capture the net effect of all that complexity in this lumped term, which we call the motor constant. And what that is really the integral of all of the B, L, and R terms that will eventually multiply current to get torque or multiply velocity to get back EMF. Because these wires are long and thin, so you can fit lots of length in the magnetic field, they also tend to have a fairly high resistance, a significant resistance that we have to consider. So that's a second motor property. Along with our motor constant, now we've got coil resistance. And to understand the third effect that we'll be interested in, let's think about commutation. So when the wire is over here, it has good leverage and tends to cause a big moment about the spinning axis. But when the wire is at the top here, you can see the lever arm goes to 0, there's no torque. And when it comes over here, it would have the wrong torque if we didn't change something. And so this little cyan element here depicts the leads to these wires, and you can see there's a gap, and they switch halfway through which direction the electrons are flowing through the coil, so that the torque will continue to be in the desired direction even though the thing is rotating. This is called commutation. And in brushed motors, it's achieved with a physical brush touching this strip. And that leads to friction. And so the third property that we're going to think about a lot for our electric motors is motor friction that mainly comes from this brush contact, also from bearings and stuff like that. So once again, if you remember nothing else from this lecture, please remember that in an electric motor, the electromechanical torque is proportional to current through the motor constant. The electromechanical voltage drop is proportional to the velocity of the motor through the same motor constant. Now, there are two other relationships that will come in handy. Now, these should be familiar, and we could derive them on our own. One is entirely in the mechanical domain, and one is entirely in the electrical domain. And so we have this torque balance. The load torque is equal to the electromechanical torque minus the friction torque. And the applied voltage is equal to this electromechanical voltage plus this IR term, this resistance voltage drop. And let's look at the mechanical relationships first. So if we take the rotor out of our motor and analyze it, and we do a moment bounce, we'll see there are three big torques on it, or moments. One is this electromechanical torque that we just talked about. And then we have this friction torque, for example, from the brushes or bearings. And finally, we have this load torque. And the load torque is coming from whatever the motor is connected to. The load torque is why we have the motor. We have a motor so that it can cause something else to want to move. In general, the sum of these moments will be equal to the rate of change of angular momentum of this rotor. And in this 2D representation, we have the mass moment inertia times the angular acceleration. Now, if we assume steady state conditions, the angular acceleration goes to 0, and we are left with the sum of the moments being 0, and it just equals all these things put together. So we get that the load torque is equal to the electromechanical torque minus the friction torque. Okay, so that's the mechanical side of the system. Let's look at the electrical side. So here we can use Kirchhoff's loop law to help us out. You may remember this from your electromagnetism or circuits course. If we start here and move through our circuit, we go from 1 to 2 to 3 and back to 1, and we add each change in voltage, they have to add to 0, because, this point can't have a voltage with respect to itself, right? So in the system, we'll model the motor with these two separate voltage drops. One is the voltage drop to the coil resistance. And we remember Ohm's law, V equals IR. So that's this IR term, that voltage is going to get smaller as you move this way. And then the second voltage drop inside the motor will be due to this electromechanical effect we just talked about. And the back EMF there, that'll be K times the angular velocity of the motor. And then, of course, we're going to apply some voltage to the motor by connecting the leads to a power supply or a battery or something like that. And so if we put that all together, we'll get that the applied voltage is equal to the electromechanical voltage plus the resistance-based voltage. Now, some of you might remember this is a big looped thing, and doesn't that have inductance? Yes, it does, but it turns out that inductance dynamics are really fast compared to the mechanical dynamics. So it's usually a very good approximation to say that the rate of change of current is approximately 0, and so we can ignore inductance effects. Okay, so that's it. We've got these two, a free body diagram and a loop analysis. That's all it takes to get our second two equations, the torque balance and voltage balance. Now if we bring this all together, we have our two new rules and our two old ones. We have that the torque, the electromechanical torque, is proportional to the current, that the voltage drop, the electromechanical voltage drop, is proportional to the motor velocity, both through this term we call the motor constant that is a function of the geometry of the motor and its coil and stuff like that. And we have that the torques must balance out at steady state, and the voltages must balance out at steady state. That's it. Now, in the topic reading and later in this video, we're going to combine these equations in lots of different ways to understand what happens in special cases and learn about how motors work. But don't take that to mean that you should memorize all those other equations. You don't need to. The only thing that you really need to know are the equations on this page. Two of them are new and you just memorized. Two you could derive for yourself. And if you sit down to try to analyze a motor or characterize a motor, the best place to start won't be in those digested equations, but instead it will be looking at these four equations and thinking about how you can use this model to figure out the thing you care about. If you understand everything on this slide, then you understand how electric motors work, period. So, and as an example of this result, we talked about this a little bit in the topic reading, but one way you could combine these equations is, let's say you wanted to know how does the torque, the output torque of my motor change as I change the applied voltage or the speed of the motor. And this equation could give you that. And that's what we use to create these motor curves. Okay, so this is a lot of information and a lot of it's new. So it helps to give our brains a chance to consolidate what we've just learned. So I'd like you to now pause the video and take at least a 5-minute break, walk around the apartment, stare out the window, have a drink of water, and then come back to continue. All right, you ready to go? So in this next section, we're going to do some exercises. So if you haven't done so already, call up your partner now. And what we're going to do is consider a set of special cases and try to explain the behavior that happens in those cases to your partner, and then listen to their explanation, and then try to work together to come up with a succinct, convincing explanation of why that special case is the way it is. And we'd like to try in these exercises to draw our intuition into this, but still use the kinds of terms and mechanical systems ideas that we've been discussing already in this video. So the first exercise tries to answer this question. When is torque maximized and why? So think about that for about 1 minute individually. Try to come up with a succinct answer to both parts of the question. Then explain your answer to your partner, listen to theirs, and work together to try to come up with a very clear, simple explanation. When is torque maximized and why? And hit pause now. All right, so hopefully you wrestled with that a little bit. When we look at these equations, it can be challenging to draw that into the language that we use to think about everyday life. So the kinds of answers that we're looking for in this case are when speed is 0. So when the motor is stalled, that's when torque is maximized. You could also say when the voltage is really high, but we'll focus here on the speed relationship. And why is it that torque is maximized when speed is 0? Well, because when speed is 0, there's no back EMF. So all the voltage can go to overcoming coil resistance, and that'll maximize the current. And the electromechanical torque is proportional to current. So that maximizes torque. Does that make sense? All right, good. Next exercise. Try to answer these questions. When is the speed of the motor maximized? And why does it happen under those conditions? Take a minute to work on it yourself. Discuss it with your partner for a couple minutes. Try to come up with a clear, concise answer, and then come back. And you can hit pause now. All right, have an answer? All right, here's an example. Speed is maximized when the torque is 0, when the output torque is 0. And that's because that torque is then minimized. Maybe it's the friction, or maybe it's 0 if you ignore friction. And if the torque is minimized, the current is minimized. And so the least voltage possible goes to coil resistance. So that leaves the most voltage possible to go to back EMF, which is proportional to speed. So speed is maximized. Make sense? All right, next one. When is power maximized and why? So here again, think about it individually for a minute, discuss it with your partner for 2 minutes, and then come back and we'll give an example answer. You can hit pause now. All right, so in this case, power is maximized at about half the peak torque and about half the peak speed. And why does it happen? Well, because power is torque times speed. And so if you're at the peak torque, then you have 0 speed and no power. If you're at the peak speed, then you have 0 torque and no power. So something in the middle is best. And it turns out, this will be quadratic with a maximum halfway between the two. We can see this relationship if we look at one of our motor curves. So here we have a plot where we have motor torque in blue and mechanical power out of the motor in red on the y-axis. And on the x-axis, we have motor speed in radians per second there. So what we can see is that as we increase the motor speed, the torque decreases until it hits 0 at the no load speed. And the power increases and then decreases, just as we talked about a moment ago, with the maximum happening at half the no load speed. And we're looking at 2 different cases here. The dotted line is without any friction. So this is an ideal motor. And the solid lines are with friction. And we can see is if we add some friction, well, that just drops the motor output torque by the amount of the friction. That's always true. And it drops the no load speed because some of that torque has to go to overcoming friction. And that reduces the amount of current available to go away to free up voltage for back EMF. And we can see that because the no load speed drops a bit, the power drops a bit. And so we go from the peak power being at half the no load, 0.5 radians per second for the zero torque case to 0.45 radians per second, still half the no load speed. But with this 10% increase in friction, we get a much bigger decrease in power. We get about a 20% decrease in power. And why does that happen? Well, because the friction is reducing the output torque and the speed at which power is maximized, both by 10%. So you get this combined effect on the peak power. Now, this is all for a set voltage, but one of the other choices we have often when using an electric motor is what voltage to apply. So it turns out that if we do a little bit of manipulation of our four equations, we'll find that the maximum power is proportional to the square of the applied voltage. So higher voltage, higher power. Now, why is it proportional to the square of the voltage rather than just the voltage linearly? I'd like you to take a moment, think about that, maybe about 1 minute by yourself, then discuss it with your partner for a couple minutes, and then come back and try to give a clear, succinct explanation. And you can hit pause now. All right, did you come up with something that convinced you? The way I like to think about it is that higher voltage leads both to higher torque and to higher speed. You can imagine that curve increases and the peak speed increases and the peak torque increases. And those two are getting multiplied by each other to get power. Another way of thinking about it is that the motor converts electrical power to mechanical power with some efficiency. And electrical power is the voltage times the current, as we learned in our physics courses. And the current at peak power will be proportional to the voltage because V is IR. And so that also gives us this V squared relationship, or equivalently an I squared relationship, assuming that we're at the optimal point. Okay, next exercise. When is efficiency maximized and why? So here again, think about it individually for about 1 minute, then discuss it with your partner for 2 minutes, then come back with your succinct answer in hand. And you can hit pause now. All right, you have an explanation you feel good about? Here's an example explanation. Efficiency is maximized at a low torque and high speed. And that's because efficiency is the mechanical power out of the motor divided by the electrical power into the motor. And the mechanical power is high in the middle, which is good for efficiency, but the electrical power is the voltage times the current, and the current drops as the speed increases. So the denominator is getting smaller as you go up the speed curve. So some middle to high speed is best for efficiency. And we can see this in our motor plots. So here we have motor current on the y-axis, on the left y-axis, and electromechanical efficiency on the right y-axis with, again, motor speed on the x-axis for the same motor. And you can see that the motor current, and again, we have no friction is the dashed line, and the solid lines are with 10% friction. And you can see that the motor current drops linearly with speed, and that's implied by our first four equations if we look at them and think about what they mean. And that's always true regardless of the amount of torque. The current and the speed will be proportional. It's just that the current won't be zero at our no load speed when we have some friction, because we'll need that current to cause the torque that matches friction. The strange thing happens when you have no friction in the motor, which is that as the speed increases, the efficiency just increases and it approaches 1 as you approach the no load speed. And that's because yes, the mechanical power out goes to 0, but also the electrical power in goes to 0. And they both approach 0 at about the same rate, and you end up with perfect efficiency. Of course, this isn't very helpful because you wouldn't be able to use your motor to do anything. If we add a little bit of friction, this 10% friction, our maximum efficiency point drops from 1 radian per second all the way down to 0.7 radians per second. So big reduction in the operating point corresponding to maximum efficiency. And the magnitude of the efficiency itself drops from 1 to about 50%. So huge reduction in the maximum achievable efficiency. So a little bit of friction really hurts the maximum efficiency of a motor and the system as a whole. Another thing to just notice in this figure is that around our maximum power point, which is halfway, the best possible efficiency, even with a perfect motor, is 50%. And with a real motor that has some friction, we're going to get less than 50% efficiency in converting electricity into mechanical power. All right, so that's, again, lots of stuff to process and think about. This is a good time to take another 5-minute break, get a drink of water, stir your coffee and stare out the window for a minute, and then come back. All right, so in the next part of this video, we're going to start to think about the implications of this model for how we use motors in our designs. And for a really thorough consideration of how to choose the applied voltage and desired motor velocity for your motor, and check for problems with overheating and things like that, see the flow chart at the back of the topic reading. But these are just some quick ones to get us started. So in the first scenario here, we're going to try to choose the set point for a robotic gripper. So let's say you've got a robot that's going to grab a thing and then it'll move around. What set point do you want to analyze for the motor in this application? Take a moment, think about it individually, discuss it with your partner. Just take a minute or two and then come back. Hit pause now. All right, you have a guess? Well, if the gripper is holding the object, it's not moving at that instant. And so the motor will be stalled. It'll have 0 velocity. And that's the set point you're going to want to analyze. Now, you might also be interested in how it moves before it gets to the object, and that would be the no load speed. And the requirements of those two tasks, moving towards the object and then holding the object, will have different implications for gear ratio, say. You'd want a really high gear ratio to grab the object, so you could have the smallest motor possible while still producing the desired force. But that would make it go really slowly. And to get there quickly, you'd want a very low gear ratio. And we'll talk about that a little bit more in our gears module. But the set point of the motor for this gripping task would be stall. And the things that would limit performance would be the peak current that you could sustain. Remember, at stall, you get a very high current, and then the motor can overheat. So that's going to be something we'll have to consider to make sure that doesn't happen in our design. All right, now let's imagine that we're designing a climbing robot. It's going to climb up the wall or something. What set point should you choose for your motor in this task? Take a minute, think about it yourself, then discuss it with your partner for a minute or two, and then come back. You should hit pause now. Okay, so maybe you notice that if you're climbing, you're trying to raise the body of the robot through gravity. So you're trying to do work on the robot. And if you want to do that quickly, that means you want to do a certain amount of work over a short period of time. That means high power. So this would be a good task to choose peak power output for your motor. So that'd be half of its no load velocity. That's where you'd like to operate the motor. And if we start to think about other things like the applied voltage and other constraints, remember that our peak power increases with the square of the applied voltage. So we'd want the maximum peak voltage, the maximum applied voltage we could get away with. And there are two things that might limit us. One would be maybe if we apply too high of a voltage, we start to damage the brushes in the motor or something like that. So the voltage itself could be limiting. And on the other side, that is going to result in a high current, which will heat the motor coil. And depending on how long our robot is going to be climbing, we might overheat, and that could become a limiting factor. So if we have to do a long climb, probably overheating will be the limiting factor. If we're doing a very short climb, maybe peak voltage is the limiting factor. Okay, next scenario, let's say you're designing a solar car. What operating point would you choose for your motor? Think about it individually, discuss it with your partner, and then come back. You can hit pause now. All right, so I'm thinking that the limiting feature here is that we're getting our energy from the sun as we're using it, so we want to be really efficient. And so we might try to operate the motor at peak efficiency, which is a medium-high velocity, a little higher than half the no-load speed. And here again, we'd probably be limited by voltage because, as we saw, the efficiency of the motor increases as voltage increases, as we read in the topic reading. And here again, we might run into limits of overheating, depending on exactly how much current we're pushing through. All right, here's another one. What if we're designing a running robot? So it's got legs and they bounce off the ground and go like that. So we're trying to choose the motors for, say, the knee joint of a running robot. What set point should we choose? Think about it individually, discuss it with your partner, and then come back. Okay, so this one is a kind of a trick question, right? Maybe you noticed that as you were discussing it, because there are lots of different operating points that we'll be interested in across the cycle. Maybe when you're at the bottom dead center of the stance phase of running, the motor isn't moving and we're really stalled. But when the leg's in the air, we're swinging it in no load conditions. And other times we're trying to push off of the ground, and so we're trying to maximize power. And in those cases, you need really to run a dynamic simulation, and selecting a motor becomes a non-trivial problem. Actually, in my laboratory, one of our graduate students is working on developing a convex optimization approach to selecting the best available motor for a given robotic system under constraints like this. And if we don't use that kind of approach, we would iteratively guess and check. All right, so here's something that might come up if you've picked out a motor and you're using it for a task, and you notice, wow, the power is a lot lower than what I wanted or expected. What should you do then? You've already got your motor and the power output is a lot lower than you wanted. What to do? Think about that individually for about a minute, discuss it with your partner for a minute or so, and then come back and hit pause now. All right, so there are lots of possibilities, but the place that I would start first is check the operating point of the motor. Is the velocity at the point that corresponds to the maximum power? And if it's too high, you would want to reduce the gear ratio, say, which would mean more torque on the motor output shaft and therefore lower speed. And that would move it towards the peak power operating point. If the velocity was too low, that means there's too much torque on the output shaft of the motor. And if you increase the gear ratio, then for the same gearbox output, you'd get less torque on the motor, and the motor would be able to spin faster. And we'll be talking more about gear ratios and all that stuff in the next topic reading topic video. But this is a commonly overlooked change that you can make, is even the same voltage and the same motor, just operating it at a more desirable velocity can lead to a big improvement in performance. Okay, so at this point, you are able to select the set point for your motor for your third project. We have all the information we need to do that well. The next step would be to think about how you characterize that motor. And if you think about the models that we've talked about today, how would you exploit those to design tests that would reveal your motor's characteristics? So the first thing to think about is, what characteristics do you care about? And here you probably want to find intrinsic characteristics of the motor that are not operation dependent, right? Then you'd want to think about what equations contain those properties, and what would you have to measure in a test, and what operating conditions would make it easiest to isolate the term that you're interested in. And you might even think about how you perform a sequence of tests, and with the results of one building on the previous. This will be something we discuss in our coaching sessions over the coming week, but it's an excellent time to start thinking about it now.